Hello, everyone. Today I'm going to make a presentation about holistic electrification compared with the deep energy retrofit for the optimal decarbonization pathway of UK dwellings, which we will make the demonstration with the case study of the 1940s British post-revolutionary house. So basically, I will have a brief introduction on the deep energy retrofit and the literatures on the building stock electrification. So for deep energy retrofit, I will call it DER. So that is a major building renovation project, which could have reduced for at least 50% for the energy consumption from the pre-renovation baseline, and the average initial investment for the energy reduction rate of 60% to 90% will be more than 330 euros per square meters. And technologies could be thermal performance improvement, like the envelope insulation, and upgrade for the lighting and electric systems, and introduce the heating, ventilation, and air conditioning systems and building automations, and also which could integrate a renewable energy system. As indicated by the standard, the achievement of the near zero primary energy consumption would have, which is also DER, would require a high initial investment cost, which is primarily made unacceptable and for the homeowners and the investors because of the high cost. And recently, a lot of research has focused on the building stock electrification. The electrification of the building it depends on the fossil fuels usage and switch to the embracement of renewables. This could be including the heating electrification made with heat pumps, renewable power, and integration of the energy storage systems. And people are focused on the negotiation between the cost, carbon, and the grid stability or security. And this involves all the key stakeholders to strike a careful rethink and look for the optimal solution without neglecting any one of these aspects. And the main challenges would be the demand response strategies, which when the heating is electrified, the peak power load would be higher than before. So there are basic strategies proposed, including the peaking clipping, valley filling, load shifting, energy efficiency, and electrification. Previous studies on the residential building retrofit. Here I have listed some references for what they have done for electrifications. So they have studied for the electrification on the space heating, the domestic hot water, and also the cookings. And for the assessment criteria, most of them have investigated the aspect of energy, carbon, economic, and indoor comfort, and also the load shifting strategies, but not all of them have integrated all of them into one research. So this figure is about the carbon conversion factor projection in the UK context, which starts from with the data from 2014 to the year of with the prediction to the year of 2040. It would be advantageous to integrate the carbon conversion factor projection from the UK's power sector and analyze its impact on the decarbonization process for building sections, and also developing electrification retrofit strategies for the future. For our research, we have proposed an innovative, holistic, decarbonized electrification retrofit, which I called her strategy, and analyze the impact of the whole house impact and its effect. And then we define a number of the HER interventions and compared with the cost optimal of the deep energy retrofit innovations. And then load shifting strategies is applied for the HER retrofit strategy with the aim to reduce the electricity demand and then contribute to enhancing the grid stability. With these things done, we will finally to evaluate and compare the carbon reduction impact of the HER and DER strategy, especially with indoor comfort on the summer heating risks. So this research is going to answer the following 4 questions. So what impact of lifetime carbon emissions on the to the HER and DER strategy, and which would be more rapidly for the zero carbon buildings? And secondly is for the which would be more cost effective. And third one is have impact on the summer overheating issues, and will they have the mitigation ability? And fourth one is the impact of the HER strategy on the grid stability, and what's the load shifting strategies and their contributions. So firstly, for the HER strategy, we have the definitions. So firstly, it's replacing the fossil fuels supplied system with a high efficiency electricity powered system. And secondly, is to upgrade the inefficient electricity systems such as lighting, smart controls into high efficient household appliances. And the third one is to incorporate and managing the standalone renewable systems such as PV, solar thermal collectors, wind turbines, thermal heating storage, and electric, like the battery storage, to enable the role of buildings as energy prosumers. And also, except for the definition for the her strategy, they are also defined for the principles. So for the HER, it should meet at least one of the following principles, and without have any adverse impact on each other. It includes reduce the equivalent carbon emissions, reduce the initial investment cost and bills, and adapt to the grid peak load capacity, the indoor overheating in summer. So basically, this 2 figures is about what kind of type would her strategy be. So it includes heat pump driven type and the electric heater or boiler driven type. So for heat pump driven type, the heat pump produced hot heat would be stored at the thermal heat storage tank, and then supply the thermal hot water for the space heating and the domestic hot water, and they can also supply for the dishwasher or maybe the washing machine or dryer. And for electric heater and boiler, the heat is directly supplied to the space heating and domestic hot water. This figure tells us about the historical and the predicted carbon emission factors for the UK national and Nottingham regional levels from 2010 to 2040. And we can see that in the recent years, the carbon emission factors um, has a rapid declines until 2020. And according to that, we have predicted for the uh, future values for the UK nations with the green upper bound lines and the gray with lower bound lines. For the red lines is the predicted values for the regional for Nottingham areas. And we can see that until after the 2030, the carbon emission factors would have relative low uh, levels compared with what is now. So these future values will be an assumption for our research. So in this, um, we have the reference buildings for the investigation. So basically, the UK is experiencing severe house shortage after the Second World War, and the post-war development period in the late 1940s have lead to the construction as the majority of semi-detached house with masonry walls, which occupied around 20% of the total building stocks. So we selected the real building as due to its match well with the reference building definitions. So for the total floor area for this building is 85 square meters and solid wall constructed without any insulations. And space heating and hot water is powered by only the natural gas, and the cooking system is by the gas cooker and the electric ovens, along with powered by all the electricity. The baseline energy consumption for the reference building is around, it's near to the 400 hours per square meter, consists of the natural gas part and the electricity part, but the natural gas is most of them. And update the measurement test to compare with the simulation results as we did. It shows that there are total energy discrepancy has the discrepancy of 3%. The measured data for the natural gas and the electricity and total energy consumption is listed here. Within 3% of the discrepancy, the simulation results is acceptable. So we use this simulation results as the further investigation. So we have listed for numbers of the retrofit measures and divided into the her strategy and the DER strategy. So for DER strategy, we have listed the two types. One is passive insulation only, and second is for deep energy retrofit towards the near zero energy retrofit. So it integrates both the system integration and also the wall insulation, the envelope insulation. And for the her strategy, so the first one is we have the electric boiler, heating driving electrification, and second is for heat pump driving electrification. And based on these two, for this strategy combinations, we have the further integration with the other technologies to be integrated. So basically, we have done the simulations for this four combination to have the compare. We can see firstly for the bottom tables, the annual carbon emission reductions for her strategy and for DER strategy. We can see that for her strategy, the annual carbon emissions reduction rates at the beginning, it's not high as the DER strategy, but it has a quite high in, in, increasing rate. So until 2031, it's like nearly to 100% of carbon reduction rate. And also for the energy reduction rate, we can see that for the average one, it's a little bit lower than the DER strategy. But the advantage is that the her strategy could lead the building have rapid step towards the near zero carbon emissions. However, the challenges existed there when we have the electrification for the whole house. Then the imported grid electricity peak load is increased a lot compared with the DER strategy. And also at the beginning of the bill reduction rate also is a little maybe lower than the DER strategy, but it depends on how we select the measures. So according to that, we have tested a lot of grid load shifting strategy. So first figure is about the building with HER strategy, but with and without insulation material. And second one at the right is we tested the load shifting strategy with PV electricity and PV with wind turbine electricity generation systems. And third one is her strategy and without the battery storage. With these three figures, we compare with the comparing of the three figures with the baseline, we see that the load shifting strategy have reduction rates of 8%, 84, 48%, and 45%. It shows that with PV and wind turbine technologies, it has the highest load shifting, reductions, peak load reductions. With the wind turbines could offset the drawbacks of the PV electricity generations when the available solar radiation is insufficient. So if integrate with the three technologies, the insulation, the battery storage, and PV and wind turbine technologies, the grid load would be reduced a lot. And then we can see the thermal comfort for her strategies with different technology to be integrated to mitigate the summer overheating issues. The following 4 levels of combinations have been investigated in this section, and we can see that in the baseline, we have listed the frequency of discomfort hours with indoor temperature higher than 25 degrees and higher than 28 degrees. The following 4 levels of combinations have been investigated to have contribution for the summer overheating issues. So we have divided into 4 levels, include deep level, moderate level, mild level, and slight level, with the highest is high insulation solar glazing replacement in the south and west windows, which could induce a maximum of 4.9 degrees of highest temperature reduce. And then we can see that, in different levels, the temperature reduced a little bit until the slight level, which is the triple glazing replacement of the window with maximum 1.8 degrees compared with the maximum indoor in the baseline. So we can conclude that although the annual carbon emission and energy reduction rates have no obvious differences in the first year, her strategy could achieve net zero energy emissions more quickly than others. Then, secondly, according to the cost optimal analysis, the her strategy could have a wide range of uh, the have a wide cost range from 184 to 613 um, um, euros per square meter compared with DER, but the her strategy could result a relative lower, maybe lower cost than the DER strategy according to the decisions. And also it could found that the cost-effective her strategy are those heat pumps, which whereas these involving electric boilers will make the worst economic performance. And the overheating issues could be somewhere mitigated according to the four levels of strategies. And then it could be concluded that the PIR insulation material with high insulation solar glazing is the optimal insulation method for the indoor thermal comfort improvement. And also, finally, to lead the reduce of the electricity load, we find that thermal insulation, renewable technology, and battery storage have the impact of 8%, 48%, and 45% respectively. So in the future, we will more focus on how to reduce the uh, grid load, the grid peak load, especially in the winter, to make this strategy more available. Okay, thanks.